All right, honors chemistry kids, we are going to talk about a couple of things today. We're going to talk about band of stability, and we're going to talk about half-lives. I'm going to also create another video where I go over the difference between fusion and fission and a couple of the ways that we use atomic power. And hopefully we can use atomic power once we get a handle on it. So the first thing I want to do is I want to review the different types of decay. Now, I did not talk about all the types of decay in our last video because there are more types of decay than we had time for. And really, in all honesty, I want you to know how to do alpha beta equations. There's an alpha decay here. This is types of decay where we have a helium nucleus emitted, the mass number decreases by 4, and the atomic number decreases by 4. So we are kicking out a helium nucleus to make that nucleus smaller. Now you'll find alpha decay when we have a fairly large nucleus. You'll also find alpha decay on some of the smaller nuclei, but they'd have to have a lot of extra neutrons. Okay? Beta decay happens when we have an electron leaving the nucleus, and it's symbolized by a beta or an electron negative. The mass number does not change, but we do increase. We take a neutron and we turn it into a proton. So we increase the atomic number by 1. Positron emission is the exact opposite of beta decay. So positron emission is where we have a beta plus or an electron plus. Okay? So once again, we have no change in the mass, but the nucleus or the proton number decreases by 1. Okay? So it's the exact opposite of beta. Positron is different than beta. And then we have electron capture. And we call it electron capture because theoretically an electron from one of the lower energy levels falls into the nucleus. And so it turns a proton into a neutron because that electron that falls into the nucleus becomes part of a proton because opposite charges attract, and it turns that proton into a neutron. So once again, we have no change on our mass, and our proton number decreases by 1. And gamma emission is a high energy electromagnetic ray. We symbolize it by the gamma symbol. We have no change in our mass number and no change in our atomic number. The thing that does change, though, is the energy level of that atom. So our energy level goes down. Okay? My next question is, we've seen that elements can decay by lots of different means: alpha, beta, positron, electron capture, gamma emission. My next question is, why are some isotopes stable and others decay? So we know that, for example, we have isotopes of carbon. We have carbon-12, we have carbon-13, and we have carbon-14. These two isotopes, carbon-12 and carbon-13, are stable. This one is unstable. Why? What's the difference? Now, I would like to look at the ratio between the protons and the neutrons. That tells us a lot about the stability of the atom. Now, normally we look at ratios, we're going to create a graph. So here's our graph. And I'm going to make this a little bit smaller so that we can keep it all on screen. Okay? So on our x-axis, we have our number of protons. So Z is our number of protons. And on our y-axis, we have our number of neutrons. Okay? You'll notice that for very small elements, we have almost a perfect 1-to-1 ratio. So this is our 1-to-1 line here, where we have neutrons to protons. Okay? Notice though, as our elements get heavier, it becomes more of a 1.5 to 1 ratio. So there's something about as the nucleus gets bigger and bigger that we need more neutrons in there to stabilize that nucleus. Okay? You'll notice also that we have color codes on how things will decay. So if it's blue, we will be doing a beta. So notice blue is basically, we have too many neutrons. So that neutron has to turn into a proton to make it stable. And that's why it is all blue on this area over here. Notice the black line here is where it is stable. But here on the other side, where we don't have enough neutrons, we will go by positron emission, where we turn a proton into a neutron. Okay? And then only really once we get way up here where the elements are really heavy, will we start doing alpha emissions. Alpha emissions, except for rare things, are really on heavy elements. We're just kicking things out, just in out of the nucleus, just in a bid to make the nucleus smaller. And then we have a few elements, not many, but just a few that are green that can undergo fission. Okay? So basically, if you have something above the stability line on our neutron to proton, we are going to have it decay with a beta decay. If you have something below the stability line, you're going to have it decay with a beta plus or a positron decay. And only when you get really, really large elements, you start seeing alpha emissions going on. Okay? So here are some questions. Here's another band of stability graph. Here it has both the 1-to-1 ratio on it and the 1.5 to 1 ratio on it. And you'll see that almost everything that is stable falls between the 1-to-1 and the 1.5 ratio. Okay? So, what seems to be the ratio of protons to neutrons that is stable? So, what we really are doing to calculate this ratio is we are looking at the number of neutrons and we are dividing it by the number of protons. Okay? And we can do that for each element. Each isotope of each element. Now notice on this, even though we have the same number of protons, we have lots of different isotopes going on. So we do that for each and every isotope of each element. And we do that for ones that are stable, and that's where we get this band of stability here. We don't count the ones that are radioactive and decaying. We only do it for the stable ones. Okay? So we notice that all of the elements that are stable seem to fit somewhere in between the 1 to 1.5 ratio. We notice that as we have smaller elements, it's closer to the 1-to-1 ratio. And as we get to larger elements, it's closer to the 1.5 ratio. So we notice that there is kind of a bit of a curve here to this graph. So we seem to have a 1-to-1 ratio, almost to 1.5-to-1 ratio. This is for the smaller elements. This is for the larger elements. Okay? Is there a number of protons that, even with the ratio of protons to neutrons in an atom, that's unstable anyway? If you go up to this very top graph, where we see how it decays, notice after 82 protons right here, 82 protons, we have no more stable elements at all. So after 82 protons, nothing is stable. Okay, so if we look on our periodic table, let's look at our periodic table really quick. 82 protons. So if I look at that, "82 protons is lead." Everything after lead is unstable, okay? Every single element past here, all of these are all unstable. They're all radioactive. They're all decaying in some way, shape, or form. Okay? So lead is the last stable element. Okay? And I just answered that question right here. Lead is the largest or the last stable element that we have. Okay, binding energy. Now, we've talked about fission, we've talked about fusion just in surface. So fusion, just as a reminder, is when we bind elements together. So we fuse elements, we fuse nuclei together. So nuclei bind together. And others are breaking apart, which is fission. So we have a nucleus that splits apart. Gotta love the bells still going on. Okay, so hopefully you know a little bit about entropy and trying to get to a lower energy level, okay? So we always want to have a reaction that releases energy. Reactions that absorb energy are not favorable. They actually take energy. So this is what we call a binding energy graph. And along here we have our mass number. Along the x-axis we have our mass number. And along the y-axis we look at the average binding energy per nucleon or per atom. Okay? So if I have a jump in this, if my energy goes up, that means we're releasing energy. If it goes down, we're absorbing energy. So let's look at fusion first, where we're putting things together. So if I put two hydrogens together to make a helium, here's helium right here. Notice how much energy that releases. That's a lot of energy being released. And if I put a helium together with a lithium to make beryllium, is that really going to give me that much of an energy release? Not really. So what really happens is two Two heliums will get together. Two heliums will get together, actually, and three heliums will get together to make a carbon to give you just a little bit more. A lithium will get together with a helium to make, it will kind of make a beryllium, but not, it would actually prefer to make a boron. Okay, so anytime that I can jump this, and if I can fuse a carbon together with a helium, so carbon plus helium would give me 16. Notice it gives me just a slight energy increase. And I can get slight energy increases all the way up here until I hit iron. And for some reason, iron is the top of that energy chart. Iron is incredibly stable. And it doesn't give me much energy to fuse iron together with anything. And then if we look at this other end right here, if I take really big atoms and I split them, uranium, and I can split it into, say, some protactinium, and let's see, what would I have left? I would have about 100. I would have some yttrium. Okay, that does give me a little bit of an energy jump. Not much, not nearly as much as fusion, but it does give me an energy jump. So I'm able to release energy. This is why fission works. Okay, so fission, wow, that's not what I wanted to do. Fission gives me a little bit of an energy jump. So notice that fission gives a small energy jump, and fusion, we usually talk about fusion, we talk about hydrogen being fused together to make helium. Notice we have a huge energy jump right there. That is a big jump. So fusion gives a large energy jump. And this is why hydrogen bombs, I don't know how much nuclear history you guys know, but this is why hydrogen bombs are so much more powerful than the nuclear bombs that were fission bombs that we dropped on Hiroshima and Nagasaki. So if you know anything about the nuclear warhead testing that happened in the South Pacific in the 1940s to the 1960s, they dropped a lot of hydrogen bombs there, and they actually totally annihilated several islands. Like the islands in the Bikini Atoll don't even exist anymore. They're gone because we blew them up with hydrogen bombs. Okay, so what happens to the energy when you put two hydrogens together to form helium? We get a lot of energy released. There is a lot of energy released. A large or a big amount of energy is released. Okay? If I fuse two lithium together to make carbon, do I get more or less energy than when I fuse hydrogen to make helium? So when I fuse lithium together, let's look at this again. Let's erase all this nonsense. When I look at lithium and I fuse it together to make carbon, so if I'm taking two lithiums together and I'm making carbon, do I get nearly the same amount of energy released that I did when I fused two hydrogens together? It's not even close, is it? So I will, no, I get less energy with fusing lithium than fusing hydrogen. Okay, so let's think about this. When I fuse hydrogen, which is essentially what the sun is doing, right? The sun is fusing hydrogen to make helium. That's the whole way the sun works. That is the most powerful reaction that we have. Okay? Notice as we go up in mass along the periodic table and fuse the elements, what happens to the amount of energy gained? If we look at that graph, the amount of energy gained gets less and less, right? This amount of energy gets less and less, okay? And the energy peak, we said it happened at iron, okay? So my question is, when we make elements, most elements are made from fusing smaller elements together because in the sun, most of the universe, almost 99.9% of the universe is just hydrogen and helium. So we know that all the other elements that we have in the universe are created in stars. And stars like the sun that are based off of fusion. So we can't, once we get to iron, that star has what we call a star death. The star can't work anymore. It can't fuse things anymore. So the star ends up dying. So my question is this going to let me scroll? How do these heavier elements get made? Because we know that we have elements beyond iron. So how do these heavier elements get made? It's going to let me write. It's not going to let me get made. So how many of you guys have heard of supernovas? So supernovas are how we get these stars that implode and they become supernovas. And there's so much energy as the shock wave goes through that imploding star. It implodes and then it pushes back out. And it creates this supernova. And there's so much energy that it actually gives us enough energy to start fusing heavier and heavier things, even though we're losing energy on those reactions. We take the energy from the energy of the imploding star. So these heavier elements get made in a supernova. Why won't it let me write? Okay. So we have two types of nuclear reactions. We have fusion and we have fission. And notice as we go along that binding energy line, fission becomes more of a thing as we have heavier elements. So along that binding energy line, we would have fusion with the smaller elements, and we will see fission with the really heavy elements, especially like uranium or plutonium. So which one of those gives us more energy in return? Fusion definitely gives us more energy. Why won't this let me write? So fusion gives us more energy for sure. Okay, so I want to stop that there, and we'll talk about radioactive series and nuclear decay and half-life.